When building a voltaic cell, we have learned that when we separate the anode from the cathode, the redox reaction takes place and the electrons take a specific direction, and that specific direction is always from the anode to the cathode. The reactants in the anode have a capacity to oxidize, the reactants in the cathode have a capacity to reduce. And we have seen that the voltage indicated by the voltmeter indicates of how spontaneous that is. And remember that for this reaction to take place, the voltage needs to be positive. Sometimes if you plug in the voltmeter and in the opposite direction, you may see this being negative. It's not because you reverse the direction of the electrons, it's just that you connected the voltmeter in the wrong electrode. But regardless of how you connect the voltmeter, you will have this direction of electrons, in this case from the anode to the cathode. That's a voltaic cell. It's a spontaneous reaction, and the reaction will stop when the voltmeter indicates 0, and at that point the specific combinations of reactants and products in both electrodes is equal to the equilibrium constant. So that's what a dead battery is. A dead battery is a battery in which the concentrations of reactants and products are such that when you multiply them, you obtain the equilibrium constant. Now let's see what happens when we add now an external source. With adding an external source of voltage, one can either speed up the reaction or reverse the reaction. When we reverse the reaction, that is called an electrolytic cell. An electrolytic cell is when the device may be the same, the setup may be the same, but now we have an external source. Now, the moment this external source of voltage is larger than what already indicated for the spontaneous reaction, you can reverse the direction. Definitely, the reaction would like to go from the electrons from left to right, but if the external source such that the external plus, if you will, this would be I'm going to put just natural, the one that it already exists, this one would be 1.48. As long as this is positive, such that you add an external source, you will be able to see a change of direction of the electrons. And notice then that what used to be the anode now is the cathode, and what used to be the cathode now is the anode. The difference in the setup is that for an electrolytic cell, the anode is positive and the cathode is negative. This is pretty much a convention, but just to indicate that the electrons are flowing in a natural direction, if you will, in the opposite direction that you would have for a voltaic cell. So let's try to understand a little bit more what this means for an electrolytic cell. It has a lot of applications, as you can well imagine. It will cost some energy, but electroplating, for example, is one of those applications. Let's try to understand it more from the chemical point of view. So let's say that you set up a galvanic cell like this one that you have here, in which, as you can see, you have an electrode of iron, an electrode of tin, and some iron 2 plus and tin 2 plus. And for the direction of the electrons, the spontaneous reaction is such that you will have iron oxidizing and tin reducing. And when all if this is 1 molar and this is 1 molar, the other ones are solid, maybe this N is not an N there, then the voltage indicated is equal to the standard one, and this one is 0.3 volts. Now, the first question is, how much external potential do you need to apply to reverse the direction of the electrons when there is 1 molar of iron and tin? Well, because what's going to indicate here when you have 1 molar is 0.3, the external at least needs to be, if you will, reverse, so let's put negative 0.3 volts, so that the total, at least external plus, let me put here of the battery, this was 0.3, so if you put 0.3 external, at least you will stop the reaction. If you put more negative, then you'll be able to reverse the direction of the electrons. Okay, so if you reverse the reaction, what changes are you going to see? Well, for the spontaneous reaction, the iron here was a reactant, so it was thinning. But therefore, if you reverse it, let's reverse this. When you reverse it, the iron will get thicker because it's a product, and the tin will thin. The tin will thin because it's a reactant. Okay, pretty much the opposite direction of what you see for a galvanic cell. Okay, now let's say that you let the spontaneous reaction die, that is, it reaches equilibrium, and at that point the voltmeter will be 0. So how much voltage do we need to apply to reverse the reaction was already taking place? Well, anything that is negative, and something as little as 0.01 volts, you can already overcome the one that was already 0. So just to apply the same equation here, even if it's 0 volts, since this one up here is already 0, you already have a reverse reaction because you have a total of a negative potential. Notice that the external potential can also be used, provided that you didn't run out of any reactant and product, that you can still apply voltage so that the reaction continues beyond the equilibrium point. So that how much would you need? Well, the external plus the battery is dead, but if you want to continue in the same direction, something as small as 0.01, and this could be ideally as small as possible or as small as you want, this will get the reaction going to the other direction, or well, to the natural direction that the battery was already going towards. So take home message: with an external potential, one can reverse the reaction or even make the reaction keep going forward even beyond the equilibrium point. What matters is what overall voltage the electrons have, so that they can move either to the right or to the left.